What's up, everyone? Welcome to Simulation. I'm your host, Alan Sakyan. Pumped to be talking about probing the cosmos. We have Luke Hawkins joining us on the show. Hi, Luke.
Hello.
Thanks for coming on the program.
I'm glad to be here.
I'm so pumped for this. And it's so cool that this is 10 years later after us going to high school together, which is so interesting too. Who we were 10 years ago, who we are now.
Long time ago, a long ways away.
Yeah. And now doing cutting edge radio astronomy, which is super interesting. We love hosting shows on space. I'm very pumped to unpack this with you. For those who don't know Luke's background, he is a digital engineer at the Green Bank Observatory, where he designs radio astronomy instrumentation, probing into our cosmos on a myriad of global projects. And you can find the main link in the bio below, greenbankobservatory.org. Also, the Facebook, Twitter, and LinkedIn profiles for Green Bank Observatory and Luke's email. All right. Luke, obviously, we've been hanging out today, catching up, talking about big questions. You know how obsessed we are with this question. What is the point of reality? Why are we even here?
I like to think that it's so that humans can someday have an empire over matter, so that we can control everything. Leave nothing to chance. I think that is the eventual end goal.
And will there be room for harmony with nature and love as we do this empire over matter?
That's impossible to know until we have the empire, but I don't see why they would necessarily be mutually exclusive.
Okay. We can lovingly have an empire over matter.
Right, just having the ability to control things doesn't necessarily mean that you step in and control everything. You can have the ability to cut down a tree and yet not cut down the tree. So to coexist, I think is definitely possible, even if we do have total control.
So in a sense, it would be to understand the reality that we are in at the most source code-esque levels, and then reach some sort of a highest possible state.
Yep, complete understanding of everything, and then eventually the ability to manipulate anything. Have no physical limitations.
Yes, nothing being impossible.
Yes, is the eventual end goal of reality, I hope.
Will we be able to poke at the initial reason why it was made in the first place, and then have a meta perspective of why this was even made in the first place?
Maybe. That would be really difficult to know. So maybe.
Does it feel like we ourselves are going to make quadrillions of simulations ourselves of
inevitably
little creations happening? And
yes, I believe humans will make many simulations, and we do simulations currently.
Yes. Yeah.
And as we go forward, our simulations will become more and more advanced.
Yeah, and indistinguishable from reality. Maybe there would be consciousness in those simulations. And maybe this is all cyclical and not linear.
Maybe we're a simulation now.
Hey, we'll get to that later in this. Then, does that cyclicity resonate, that rather than thinking linearly, that cyclically speaking, that there has been some sort of an evolution from simplicity to complexity, and then complexity just makes more simplicity, and the cycle continues?
It really kind of depends on the timescales that you're talking about, and kind of the scale that you're talking about. When you're talking about a cycle that has maybe the age of the universe, I don't know if we can necessarily point and say it will go throughout the arc of the history of the universe, that we will have many cycles of complexity and simplicity. But I think on smaller scales, you can see these cycles possibly.
Okay. As we're in this subject of the grandness of this time scales of the universe and the size of the universe and the cosmos and probing into them, we have evolved quite a bit from our initial days of just foraging for food and observing, without tools that were so scientifically advanced that they could actually see stars and planets quite well. Not only our own in our solar system, but beyond that, and also see other aspects to the cosmos that even our own eyes cannot detect. So now we have built those tools, and now we are probing into the cosmos at unprecedented rates. And given computation has also made this so much better as well. This has been a trend that you are now immersed in, and you get to see firsthand. And you got to see 3.5 years now.
Yes.
At the Green Bank Observatory in Green Bank, West Virginia.
Yes.
Using the Green Bank telescope.
Yes, the Green Bank telescope is a very big instrument. It has a collecting dish that is 100 by 120 meters, parabolically shaped. It can receive radio signals from 100 megahertz to 116 gigahertz. It is fully steerable, fully movable. It is quite an engineering marvel. And we use it to probe some of the universe's most difficult secrets.
So this was built in 2000.
Yes.
And prior to that, we were also doing radio astronomy. Let's do a breakdown, okay? We're going to get into all of the nuance that you just described about the Green Bank telescope, and this is specifically radio astronomy.
Yes.
Okay. Let's also break down other types of probing into the cosmos as well. So probably the most familiar one is like the Hubble telescope.
Yes, that's very popular.
So let's explain that, and explain like how that and how like other like transit photometry methods work, like what a Kepler and TESS and what they're doing, and then how this is different and what other methods there are, because there's like ultraviolet and there's all these other crazy aspects to the electromagnetic spectrum.
So astronomy is primarily an observational science. So that means that we look. We cannot set up as many experiments as other fields of science, but we can look. And so there are optical astronomy platforms that people know, fairly well, like the Hubble telescope and any other telescopes that you would think of, Galileo's telescope. And how radio astronomy differs from optical astronomy, and how all those other astronomical instruments that you mentioned differ, is that you can look at the universe through these different different wavelengths. So optical astronomy is done at much higher wavelengths, at optical visible wavelengths, so in the terahertz. And so as you move your observational frequency down into the RF or the microwave or the IR ranges, you can see different things. And also we know that the signals at some of these frequencies are not as affected by, say, clouds or other perturbations than optical frequencies are. So we can look at the sky even when it's cloudy with radio astronomy.
Mm-hmm. That's a synthetic aperture radar, right? SAR?
So there are a few different ways you can do that. I can't comment too much on SAR.
Okay. Which is so interesting, being able to do things like look through clouds when you're using ground-based telescopes. This stuff is, super important. Let's pass some time on this as well. Like optical astronomy mostly being used to view stars, mostly being used to view planets, light reflecting off of their host stars onto that planet and then into our photometer that we're using to measure that light. That's what mostly stars and planets for optical.
Really anything that's visible you could see. I can't comment too much on the percentage of time that optical telescopes spend staring at stars versus planets versus gaseous clouds.
Asteroids.
Yeah, so
different stuff. Okay.
We can look at whatever you can see, we can look at.
Okay.
And as far as how the percentage of time breaks down, I don't know.
Okay. And then now, this is a very classical question, but like, why radio astronomy? Like you had, optical astronomy, radio astronomy, why even in the first place astronomy, and then why radio astronomy for you? And then we'll get into more of the nuances.
So the advent of radio astronomy actually came on accident. It was, I believe, an engineer at AT&T Bell Labs who discovered that he started getting static when the sun came up on it, or I believe it was when the sun came up, he started getting static on his antenna at his house, and he noticed that the static started coming like 6 minutes earlier every day, and so he was able to deduce that there was something outside, or that the sun was giving off radio energy, or that the galaxy was giving off radio energy. And so it allows us to see things that we could not see optically. It allows us to probe questions that we could not probe optically. And yes.
So then you wanted to probe what we cannot see optically. And that was what kind of got you excited.
Yeah.
Okay.
And also the book Contact by Carl Sagan.
Yeah. Yes. So what do we like, what then are we, okay, what are we looking for with radio astronomy then? Anything that isn't in, like, let's break this down. There's a visible light spectrum to us in the electromagnetic spectrum, and that's 400 nanometers.
The
wavelength to like 700 nanometer wavelength. 400 being closer to red, and then even beyond that being closer to radio.
No, it would be the 700 that would be closer to radio.
And 400 being closer to ultraviolet. Yes, fast.
Yes.
Fast. Closer to ultraviolet, 400, 700 being longer.
Yes.
Longer wavelengths. Okay, at those longer wavelengths, once we get beyond 700, then I can't see it.
Correct.
And that's what the little remote controllers for your TV and stuff
infrared,
like that.
Yes.
Okay.
They work at an infrared frequency, so you can't see it with your eyes. but it is light.
It's light.
It is light.
So that's a stream of photons that are being emitted from the remote controller to the TV.
Yes.
That I can't see.
Yep.
And that's using infrared. Yeah. Okay. Beyond a 700 nanometer wavelength. Okay. So now, where is radio past that? And then what is the process of building a telescope to try and look in the cosmos for radio waves? And why are we even what are we looking for?
So, what are we looking for? Well, there's a lot of different science cases, a lot of different science questions that we're trying to answer at the Green Bank Observatory. We're trying to answer how stars are formed, what kind of environment sets the table for star formation. We're trying to discover new pulsars, characterize and study various galaxies and all sorts of astronomical events within our solar system and outside of our solar system. So there's a lot of questions that the scientific community doesn't have answers to, and we're trying to find answers to as many of those as possible. So
then technically we should have a telescope for every single possible slot in the electromagnetic spectrum pointed up into the cosmos.
Yeah, ideally, if you want it, you would have full sky coverage across the full bandwidth.
Full sky coverage, full bandwidth.
Yes. So the bandwidth is what we call the 100 megahertz to the 100 megahertz up to the optical frequency bandwidth.
And 100 megahertz being
the lower limit of what is observable with the GBT.
Interesting. Okay, and you listed star formations, observing galaxies, pulsars. Why are these things, what do galaxies and pulsars, star formations, what do they emit during, what are they doing? How are they emitting radio frequencies that how are they doing that process, and then what are we seeing when we capture those and try and analyze them?
So the emission mechanism is different for each of these events as far as how they actually emit the radio signals. So I can't comment too much on these specific mechanisms, but I can say that it is different for each of these for these different types of astronomical sources. And as far as what we actually see when we look at them, you would see, there are different molecules in galaxies are made of molecules, and these different molecules emit different frequency tones of signal. And so, say if you were looking at a galaxy, you could see the tones that represent the compounds that the galaxy is made out of. And so those would show up essentially as like a line, a solid, like a line on a waterfall plot. Whereas pulsars or some of these transients, like pulsars or FRBs, their signature is more of a pulse or a beep. So rather than a solid line, you would see a beep that covers more bandwidth.
So we can view at a molecular level frequency tones of a galaxy distant from us and say what molecules exist in that galaxy?
Yes, and we're getting more and more precise measurements every day.
Okay, and then that type of signal processing at at GBT, a Green Bank telescope, looks different than a pulsar signal processing.
Yes.
Okay, so different algorithms are being used to process the radio frequencies for the specific use cases for star formations or Milky Way molecules or pulsars.
Correct. So,
Okay.
So for some of these sources that aren't changing in time, like the galaxies or stars, like these are things that do not change. The galaxy is still going to be the galaxy. Its compound is not going to be, or its compound makeup is not going to change over, a time span of hours. So what we can do is you can average all the data for many hours of certain observations and compress that into a more dense data package. Whereas for some of the more transient sources, you need the higher time resolution to be maintained throughout the signal processing chain.
Yeah. Wow. So basically you're, in a sense, it's this big radio frequency bucket that you're holding and pointing to the sky, and then you are holding it there for long periods of times in many cases to try and watch something for a long period of time, and other times you're just looking for a short bit of time to identify the one thing that you need and move on. And these are the different experiments that you do there. But before maybe we get into more on the experiments, I also want to review these numbers that you were mentioning to us a little bit earlier. Okay, so this is 100 meters in diameter of collecting area.
Yes. It's very large.
So I think you told me that this is this a football field?
Yes, about the size of a football field.
Oh my goodness. Okay, so this is the size of a football field. Now let's okay, obviously the dish is the 100 meter collecting. That's how you're collecting the radio frequencies, right in the dish formation. And then there's an angle. There's like you could use a joystick or something to literally angle this puppy wherever you want in the sky. It's like that mobile.
Yes, not a joystick, but yes.
Yeah, it's not a yeah, a more complicated joystick.
Sure.
Okay, and then that's nuts. So then you're moving this. Do you know the weight?
I believe it's like 17 million pounds.
You're moving like a 17 million pound object, and you have to make sure that it stays in good, healthy, fluid mechanical ability over time, which is why you need probably lots of repairs and technicians and engineers to just be doing that all the time. Lots of maintenance. But it's cool because you can upgrade the hardware over time. Right.
Yes.
This is very interesting because when you send shit up to space, you can't upgrade the hardware.
No.
But when it's on land, you can at least upgrade the hardware, which is nice over time as things get better. So then, what is the big? What's it called? It's the. This is the. It's an unblocked aperture, so so unblocked aperture meaning the actual the radio frequency collection is unblocked.
Yes.
Okay, but then what is that big giant thing that is jutting out from the side of from the edge of the dish?
Up top?
Yeah, in this image it would be from that's the highest in this image, yeah.
Okay.
What is that that's jutting up?
So that is the feed arm. So the way the telescope works is the large dish is the main collecting area, and then at that point the main dish focuses all the energy upwards in this image to either one of the receivers or to the prime focus collecting dish, which then focuses it again into one of the receivers.
So let's look at this. So then the main collecting dish is then focusing the radio signals onto a processing unit.
It's focusing the signals onto, say, a dipole or a horn antenna, and then at that point it goes through the analog signal processing chain. After the analog signal processing chain, it is then digitized, and then it goes into the more full comprehensive signal processing.
So first analog signal processing, then digital signal processing, and the collection is, in a sense, you said it's focusing it onto that analog signal processing.
Yes.
Interesting. And so then, in a sense, this is like on when you do optical astronomy, this is when the light comes in and reflects off of the mirrors, which then
a way to focus it,
and then it focuses it on that little tiny, like silicon, reading instrument analysis.
The
CCD standing for again?
I don't know.
CCD. Okay. And so then that unit then processes the photons that it received. It begins to digitizes it. Oh my gosh. Okay. So that is that. What do you guys call that part of the telescope? The arm. The dish, and then the
arm.
The arm, and then this part where all the signals are being processed, then that sends after analog to digital signal processing. Then that is what you guys get as a readout on your computer.
Yes. So it is then the digital signals that are stored and analyzed.
I'm so curious as to the algorithms and also the, like, of course, the complexity of actually taking, data of radio frequency data from galaxies and from star formations and pulsars and being able to try and make sense of that, and how you guys actually, like, really just, how do you freaking know that it's actually that? Like, holy crap, like, how do you know?
Well, so the data is coming very fast. We deal with very high data rates. So that is part of the challenge. And then once we can process the data, I mean, you can say, look at a source, and if you look at a source, take some data on a source, and then look at the data, and if the data says there's a source there that we were looking at, then you kind of know that you did something right. And if the data says no source, you weren't looking at anything, then you know you got something kind of wrong.
So you're already pointing at specific areas where you're kind of doing trial 2 or trial 3 or 4. You're testing it over, you're doing the scientific method.
Sure.
You want to make sure that the evidence is coming in. Well, it's hard if you're like a pulsar may only happen, or a star formation may only happen once in that given area where it's happening. But then the Milky Way itself will continue. You could continue analyzing that over time, stuff like that. Okay, what is up with the whole this frequency range, 0.1 to 116 gigahertz? So that's the length, the wavelength.
So that is the range of frequencies that we are able to observe. So you can convert the frequencies to wavelengths using the speed of light and an equation. So I don't know those off the top of my head, but yes, that is the range of frequencies that we are able to observe with the GBT.
What do you see at 0.1 gigahertz, and what do you see at 116 gigahertz?
You see a lot of things. I couldn't comment too much on specifically what we were able to see at the different across. I couldn't break it down for you into the different tranches of frequencies.
Okay, because it seems like that's huge. But in order for you to be able to do that, you have to be in a radio silence zone. Green Bank in West Virginia is a radio silence zone.
Yes, we are in the National Radio Quiet Zone and the West Virginia Radio Quiet Zone.
No cell phones.
No cell phones, and actually these zones, these radio quiet zones, they are made of kind of conical sections, so that have stricter rules for the sections near the center and laxer and laxer rules as you get further and further away. So, for example, within a mile of the GBT, you're not even allowed to have spark plugs. Every vehicle that goes close to the telescope needs to be a diesel.
Wow.
Yes. So once you go a mile away, then you're allowed to have spark plug cars.
Interesting.
At my house, I'm not allowed to have microwaves. I'm not allowed to have Wi-Fi. I'm not allowed to have a Roomba. Or cell phones, of course.
Yeah. Wow.
And then once you get even further away, some cell towers are allowed, but they need to be coordinated with the observatory.
Wow. Yeah. So it's in a sense you're doing your best to make the as much signal as possible and decrease as much noise, which is why you have these quiet zones, radio quiet zones. Interesting. And that's why we put telescopes up in very remote locations that are very high elevation as well. Decrease the amount of light pollution, decrease the amount of noise that could potentially happen.
Yep, and atmospheric perturbations.
Yeah. Are there radio telescopes in space?
Yes. Let's see. There was a Russian satellite that I believe just went offline earlier this year, and I think Germany is launching another one.
Yeah. Okay. Yeah. Okay. This is obviously an extremely difficult engineering feat to shoot up a telescope into orbit, or into one of these Lagrange points, etc., and like to be able to actually keep it there. These are very expensive things, and but it's crazier because you get better signal. There's less noise when you're in space. Yeah.
Exactly. Less microwaves, less spark plugs in space.
Yeah. Until that one microwave just comes flying through the space. I'm very curious. This is probably one of my favorite parts to it, which I'll actually. I think we should get to the crowdsourcing stuff right after this. I want to hit this one first because since we're actually talking about radio frequency interference, I want you to teach us about this. There's all these different measures to decrease RFI, radio frequency interference, all these different measures. But most recently, this machine learning, this ability to identify patterns and then take those patterns as noise and eliminate them so that you can keep as much of the signal as possible. And you yourself have been going deep into the machine learning to be able to do this. You were one of the co-authors on a paper on it.
Yeah, so one of the things that we're doing at the Green Bank Observatory to reduce RFI, in addition to banning spark plugs and microwaves and certain kinds of lights and all of those fun things, is we're also developing digital signal processing algorithms that will help us identify and remove RFI at these extremely high time resolutions. Currently, RFI, despite our best efforts, does contaminate the data. We do see RFI in in our observations, and we expect to see more and more as time goes on with SpaceX's Starlink satellite project and Amazon's Project Kuiper satellite project, self-driving cars with radar, the Internet of Things, Bluetooth connectivity everywhere. RFI is coming for us, and I am trying to build some gates with machine learning. So we've had really promising results so far. It's a tremendous amount of data to go through to even just validate these algorithms on. It is a tremendous amount of testing that needs to be done, and a tremendous amount of computing resources that is necessary.
When you're talking about this explosion of radio frequency interference, to me, I'm always wondering, like, how are we going to be able to, like, what are we foreseeing as long-term implications of some of these things that we're doing? Like when you throw up this fleet of tens of thousands of satellites into orbit, when you have all of the autonomous vehicles or the 5G technology or the Internet of Things everywhere, like, can we like test some of these things in like a small zone first to, like, this is what the whole digital twin and simulations come in handy, where you can, like, simulate out what actually happens first before you implement it here in this physical world. Because otherwise you have this, like, how are you going to be able to conduct your science, and who else around the world is impacted, who, like, can't conduct their science anymore due to other people trying to advance their science? This is a weird.
So in an ideal world, yes, any object that generated RFI would go through extensive compliance agreements with various observatories, but these are serious. But these projects that generate the RFI, like Starlink and Kuiper, these are serious business ventures with serious money on the line, and they get approval. So,
well, yeah, and they have big promises for delivering great things to civilization.
Yes,
and that's why.
So it's a balance between the two, and at the moment, we're just trying to develop new algorithms to help us coexist.
Yeah. Yeah. Interesting. Like, as though this one scientific party that's being more seriously influenced by it has to, like you said, develop algorithms to offset the RFI of this scientific advancement so that you can continue doing yours. It's very interesting how these things play out like that. Wow. And it's also just the big question about, like, where we're going in our future in general, but that's some stuff that we may talk about in a little bit. Something that is probably one of my favorite parts about all of this. Obviously, it's much more difficult for me to understand the complex algorithmic computer science of taking off RFI. That's much harder, but this is much easier for me, and hopefully for other people, is crowdsourcing of ideas for the Green Bank telescope and for all of these incredible telescopes that we have. Like, literally, is it really like anyone in the world can submit an idea for like a couple hours on the Green Bank telescope, and then you have a committee that'll be like, this one gets an 85% and this one?
That's exactly the way it works. Is anybody can submit a proposal for viewing, and then we have a committee that goes through and essentially evaluates and grades and ranks all of the proposals. So yes, anybody, you don't even need an astronomy background, can submit a proposal, and if it's deemed to have merit, it will get the time.
Interesting. And then what have you seen coming through? Like, has there been like universities or other governments from around the world, or some some complete like independent people that are just wanting to conduct interesting science? Like, what's been like, I guess, the percentages?
So I can't comment too much on the percentages, but what I can say is that it does seem to be mostly universities or people affiliated with universities that end up submitting and getting approved for these.
And then what are they like asking to do? Like, what kind of studies are they like star formations, or what do they want to look at?
So we do a
usually?
wide variety of science at the GBT. So like you said, we study star formation, we study pulsars, we study gravitational waves. We even do some observations for SETI. So you can provide observations for a wide variety of science use cases.
Okay, and then you give them the data.
Yes.
Okay, you just pass along the data is what you're doing.
Yes.
Yeah. Interesting. Okay. This seems like a really good way to potentially, like, I love crowdsourcing of ideas. So, so then what does this look like if if you have something so powerful that can potentially probe into the cosmos at one of the highest levels on the entire planet? Are you guys oversaturated with proposals? Do you guys get too many proposals, way more than your 6,500 hours that you're doing per year?
Yeah, so I believe that we do get more applications than we have time to satisfy. So we are oversubscribed.
Interesting. What would make a radio telescope even more badass?
Flame stickers on the side? Well, I mean, the easy answer is you could always make it bigger. You could always put it in space. You could always increase the possible bandwidth that it could receive. There's all sorts of variables that you could tweak
To increase its badassness. Yeah, interesting. How about okay, on a funding level, this is also something that I think is extremely important to talk about. So this is funded. This is the funding. The funding for this is only $10 million a year annually. Is the funding? It's all you need to run the Green Bank telescope, and you guys have like 150-ish people there.
Yeah, that all sounds right.
50 interns-ish, or summer people come over, so it increases by that. And is it all funded? What is that organization called? The American
Associated Universities.
Associated Universities Inc. AUI. Associated Universities Inc. And then the National Radio Astronomy Observatory, NRAO, and Green Bank Telescope are both under that parent
Yes.
organization. Okay, and then the funding is federally through the National Science Foundation.
Yes, the vast majority is.
Okay. And then, so that's taxpayer dollars that fund the National Science Foundation, which then distribute, we were looking it up somewhere around like, I think $8 billion or so to a myriad of scientific projects, including Green Bank Telescope as one of them. So it costs like pennies from each of us to do things like fund this, which is like a sip from a glass of beer or whatever, a bite of your sandwich.
Yes.
Like, come on. Like, one bite of your sandwich is like adding significant scientific advancement into our world. So, yeah.
Yeah, and I believe that the GBT detected a planet made of diamond. So I think it'll pay for itself if we ever get a space tugboat who can bring us back this diamond planet.
It'll pay for itself by finding a diamond planet. Oh my goodness. Okay, so this is obviously crucial. Just funding scientific advancement and scientific projects like this is such a cheap thing from each of us to contribute several pennies. This is actually also something that we're trying to figure out with media as well, because this is something that is like, we care so much about content being completely not paywalled, period. No paywall ever. Yet at the same time, it's like, yo, you give us $1? Like, if you love watching this, like, give us $1, give us $10, like the links are in the bio, and these are the little things that you can do to support like independent media or independent science, etc. Or government funded science, even just really rally for more scientific funding, or in this case, funding the independent artists around the world that people believe in. This is a very important thing. Like, you look at like Lorenzo de Medici, you look at like Michelangelo getting funded, you look at these patrons to world leading artists and what could be, rather than this like hoarding mentality and like buying a fifth yacht and a fifth watch and like all this other kind of stuff. We're very passionate about that, Luke.
I would love to have just 2 yachts. I think that would be enough for me.
You're ridiculous. I'm here trying to like patron artists around the world to become their full selves, and you're like, 2 yachts. Oh my goodness. Okay, now you gave us a little bit into this. You were talking about the study of pulsars. We haven't talked about this one yet. Fast radio bursts, FRBs. Like, what are we trying to discover with these things? What kind of, like, what does it tell us about the cosmos?
Well, so FRBs are kind of a mystery right now. I don't think that anybody knows for sure what it is that is what they are. So on the radio astronomy side, we can see pulses, and we have seen so many of these pulses that we can't explain necessarily where they came from, and we group them together and call them FRBs. And so while we don't know exactly the mechanism that causes these pulses, they are kind of mysterious.
So this also kind of sounds like it's like the cosmos is a big mystery to us, and then we like take in these little tiny like bits of data, these fast radio bursts, and then we say, okay, let's try and take these little tiny bits of data and like group them together to try and understand them better. So it's like getting tiny little like whispers from the cosmos in different ways, and you're like trying to look and like be like, what does this mean?
Yeah, the universe is a big problem. You have to break it into small pieces.
Yeah. Okay. Okay. Other thoughts on what, on all of the different aspects to radio astronomy that that we may have missed before we get into these other questions at the end. Do you feel like we should hit another aspect of radio astronomy?
Well, I just thought I would say that it's a very international aspect of science. There are radio astronomy observatories all over the world. Chile, South Africa, Mexico, China, plenty others that I am forgetting, but there are. It's a very international science.
I'm really happy that you brought that up. If we want more global cohesion and collaboration, what a great way to do it by like open notebook science style collaborations to build a more cohesive, collaborative social fabric around us. Yeah, it is a big global effort. There's so many different, especially astronomy. Astronomy itself is a very specifically like quite a more like global perspective in terms of trying to advance a science. Whereas like if you're in your like maybe biology lab trying to do genetic engineering or something, you're like, how do I like?
Yeah, we all share the stars. I mean,
Yeah.
can't share lab equipment so easily, but we can share the stars.
Yeah. I like that. That's a great point. I'm glad you brought that up. And hopefully it can do things like catalyze that overview effect where we all realize, like the pale blue dot of Carl Sagan, just that everyone and everything that's ever lived that we know of has been here. So like, please collaborate, please work together effectively. Yeah, it's been a great journey, and it will continue being an incredibly interesting story that unfolds. Yes. Okay. Any other thoughts on radio astronomy before we get to the questions?
It's very interesting.
Yeah.
I urge everyone to read more about it.
Yeah, no kidding. Especially like Luke was telling me about like living out there for 3.5 years, and then you're just like, I want to get an apple, or like a mango or a pineapple or whatever you want to get, or like use a cell phone, but like
you have to drive an hour to buy a pineapple. Like, I love pineapples. I don't want to drive an hour one direction to get a pineapple. But it's a sacrifice I make.
Yes. This is also like boom, like those types of sacrifices to, yeah. There's like all those nuances that you talked about regarding, like only being able to drive the diesel cars within a mile of it, like no spark plugs. This is very interesting stuff. No microwave, no cell phone. Like there's sacrifices. Like yeah.
And because of those sacrifices, the town around the observatory is a very small town, hence the lack of apples and pineapples.
Hence the lack of apples. But you got to know the people. You get to know the people. Yeah, you get to know the environment around you. Okay, let's dive into questions that we like asking at the end of the show. The first one, given the fact that we're probing the cosmos, we must ask, where is the space economy heading? We're going to actually be sending people to celestial bodies, maybe towards like the end of our lifetimes, and these like the kids of maybe our kids and the Gen Z kids, maybe they'll actually get to go to the celestial bodies. This is going to trigger the whole space economy thing. And
I don't know, but I would definitely like to see a colony on Mars or the moon in my lifetime.
Yeah, likewise. Yeah.
I would definitely like to see, colonies in other solar systems in my lifetime. That might be a stretch, but...
Yeah, me too. Yeah.
Those are pretty far away.
Yeah.
But for sure, I'm very optimistic about the future of space.
Yeah. Yeah, and that's one component is doing this settlement into the cosmos, and another one is just like space economics in terms of like who's bringing these payloads up into the actual space and then into orbit, and then what are those satellites actually doing up there? What data are they collecting, and then who's gaining access to that data? How are they observing the planet? When we collect that data, is it for there's some really interesting like use cases with data that we collect from satellites, like observing deforestation or observing ocean acidification, or there's all different
Exactly. Yes. Ground Earth monitoring satellites for scientific applications has so many uses. Weather forecasting, climate modeling, or climate studying. Yes, so many uses. Yeah.
Earth modeling. Earth observation from space.
Like climate. Studying, how many trees there are.
Yeah, exactly. Yeah, and hopefully also used for the purposes of benevolence always. Rather.
Always.
we got to ethically and morally and spiritually advance fast enough as our technologies become godlike in order for us to make it through the little pinhole that is approaching of the exponential technology age. Do you feel similarly?
I might say it's a little larger than a pinhole, but yeah, it's, I hope we're responsible in the future with our technology.
And what would you say is like a core like principle that we can embody in order to make sure that that we are responsible with our technology? Ori, so many giggles right now. Ori's on the giggle bus right now.
My bad, guys.
What's funny? What are you enjoying over there? You're so happy.
Well, it's not super related to the topic at hand, but I have this reoccurring image in my head of Alan in a funny position.
Ori has a reoccurring image in his head of me in a funny position. That is Ori's giggle bus right now. Okay.
So as far as how to limit the bad effects of technology,
Yes.
I would say that some important things to do would be to think about all the effects that the technology would have before you implement it and try and limit or completely eliminate any of the negative effects. And secondly, once a new technology is implemented, would be to continually re-evaluate the effects of the technology, and have that be a loop where you evaluate the effects, you adjust your operation of it, and so on and so forth.
Yeah. Yeah, I like that. That's crucial, and then I think there's even something that's even more first principled than that, which is this evolution of our own consciousness prior to making the technology. Just how can we be traumatic and then building technology? It's inevitable that when we carry hatred rather than love, that we're going to build something that then catalyzes malevolence. I mean, it's just like roots, and roots are for me. Know thyself, work on yourself, be love, be kind, and then work on building all these technologies and doing this feedback loop and deep connection to each other and to nature and to why we're here, all this type of stuff.
Yeah, sometimes I might do some work before the coffee fully kicks in, and so maybe I might do some work when I'm not fully kind, but once 10 a.m. kicks in and the coffee kicks in, I do all my work when I'm kind.
That kind of also gets us into the exponential technology age in general. What's something that like young kids should embody as they go into this age?
Say flexibility, adaptability. The technology is, like you said, accelerating exponentially. You don't know what you will need to know 5 years from now, so be ready to adjust.
Yeah. Damn, that retraining is nuts. Like we're talking like we've known long careers for a while, and I mean AI is eating our world, and in the ways that we ourselves are going to be applicable creatively, the windows are closing. Actually, we can't make as many permutations of creative solutions to complex issues as quantum computers can. There's a lot of stuff right there. How do you feel about it?
Well, quantum computers are on their way, but they're not quite here yet, I would say. So there's still plenty of room and plenty of jobs for creative, talented humans, and I don't think that's going to change in my lifetime.
It'll definitely change a lot in your lifetime. In 50 years, in 2070, there's going to be AI everywhere.
There's going to be AI a lot of places, but 50 years is a long ways out. It's difficult to make these predictions about what will and will not be obsolete.
Sure, it just really feels like it'll be hard for people to find meaningful, creative things to do every single day.
But people have been saying that too. Every time there's a kind of an industrial revolution, people say all the good jobs are going away.
Fair, but not at this scale. This is a We'll see.
We'll meet up again in 2069?
2069.
50 years from now.
Yeah, we'll see, and then we'll replay this episode. We'll jump right in. Yeah. We're not even going to need to be doing the talking. All these ideas will have already worked themselves out.
And maybe I'll have 2 yachts.
Oh my gosh. And maybe we'll have patroned millions of artists around the world to pursue their creative passions.
Yes, before the 2 yachts.
Maybe all of them can come and hang out on the yachts and do their art. Is humanity a biological bootloader for digital superintelligence?
Maybe accidentally. Maybe it will turn out that we were accidentally that, but we'll see.
Not like a determined, just an accidental. It may be that we stumble into building digital superintelligence, but
exactly,
not our destiny, as all we did for the last 5 minutes was talk about AI taking over everything, and now it's like, oh, it's going to be an accident. Like, come on, like, it's pretty much like we were just talking about it so vehemently, like with such gnosis, and now we're like, oh, it might be an accident. Like,
no, well, so I guess that depends on how I interpreted your original question.
Mm-hmm.
Is, are we here to be bootloaders? Like, I took that as, were we placed here with the intention of just being bootloaders for a digital superintelligence?
Mm-hmm.
And I say, no, we were put here, I don't know, but we're here, and we might end up just accidentally being bootloaders for digital superintelligence. But
what were we put here by?
The Big Bang.
What made the Big Bang?
I don't know.
If science gave a little bit of room for mysticism, magic, spirituality, they could potentially harmonize better on complex questions like that. Do you feel that way?
Maybe. I don't necessarily think that it's science's responsibility to make room for that, though. I think science is what it is.
Science has plenty of room for intuition. A lot of people intuit what's beyond the edge of science, and they plant some sort of like a flag way beyond the edge, and then they do rigorous science over decades to get closer and closer to that, and then they go, that intuition was right.
Yeah.
So that's where intuition or spirit or feeling or emotion or all these other sorts of ways of interpreting some sort of a divine connection to this feeling that I'm having about something, and then being able to say, now is it possible for me to scientifically work my way to that I've hypothesized? And that's, I think, this room that I'm talking about.
Maybe. If you want, I would call that a hunch, I guess. You could have a hunch that something will turn out this way, and you would call
Intuition?
it a spiritual hole,
It's so
a spirit-sized hole in the donut of science.
It's almost as though like this word like hunch is like trying to, in a sense, just be like, how can I like avoid like spirituality or like, intuition, or, it's like, just call it like what it is. Like, so many scientists before us have been extremely spiritual and they've made tremendous advances. And I think this is, again, I think these two things marrying is a big part of our ethos, and it can potentially lead to it's so funny because science in many ways is just catching up to what people over the last hundreds of thousands of years have been aware of. Really, like the deep interconnectedness that people have to the land that they're on, to the animals and plants, and to each other that they're in tribes with. This is something that's ancient AF, like hella far back, and like only now are we looking back and saying that, oh, now we can scientifically prove that when you go into a forest that your cortisol levels decrease. So you should spend less time in little rat boxes in metropolises, and you should spend more time in forests because it's healthy for decreasing your stress levels. It's like, really?
Well, to be fair, they had fewer rat boxes in metropolises thousands of years ago, so.
Fair, yes, the cultural analysis of that. Yet at the same time, it's like, just even that in itself is like, really? We need to have a rigorous, like, like, have we really become so disconnected and so separated into our own egos that it doesn't register that me feeling empathy, or me asking this first principled question of why I'm even here and what is this reality that I'm a part of, or how do I connect with the environment that I'm in? Why does it feel like my stress levels decrease when I'm immersed in nature? All these types of things. Really? I mean, like, if science and spirit could kind of harmonize on that a little bit more, we could move the edge faster.
Well, I'd be the first person to say that I don't know everything, so maybe there is more room for it than I'm giving it credit for, but maybe not.
Yeah, I will also agree that I am just know very little, and that I would also like to just urge people to care more about the marrying of science and spirit and where that could potentially lead us.
Yeah.
Do we have free will?
I think so.
And what gives you that thought?
I feel pretty free in my life, I guess. I do. Sometimes I feel free, so therefore I am free.
What is consciousness?
The ability to doubt.
Why do you pick that?
It was the first thing I thought of, and it just strikes me as a very, I don't know, kind of not necessarily human, but a very biological thing. Like, computers don't doubt, but humans do. And so maybe once a computer could doubt, then it could be said to be conscious.
Interesting.
But to have doubt in yourself, or to have doubt, maybe doubt in yourself is what consciousness is to me. What do you think it is?
Everything. Everything is consciousness.
So, do you think this is conscious?
Yes.
So there is nothing that is
not conscious.
Okay.
Yeah. We are that. We are all that. Are we really all one?
Is that a question?
How do you feel?
I feel good.
Are we all really one, Luke?
We may be. I think each person is an individual. I think each plant is an individual plant. Is there something deeper, something hidden tying all these individuals together? Maybe. Maybe not. It's something that I don't know enough to even guess.
Do they all come from the same source?
All the individuals?
Yeah.
In what sense?
Do all of their lineages go back to the same source? Did it all come from one?
I honestly don't know. From one Big Bang.
Is that a one? Is the Big Bang a one?
I would say so.
I don't care what people want to call it. Big Bang, source, God, creation, infinite consciousness. I don't give up what people want to call it. Just commune with exactly that, and all of our problems will be solved. That's how I feel.
I think that, if nothing else, is a very good start.
I feel really good. Feels like when we were first talking earlier today about interconnectedness and diving into that. That was very interesting. And here we are again on the show talking about oh, man.
Are we connected or just affected?
No, that was your point. Is this a simulation?
I don't know. If it is, it's a pretty good simulation. But I don't have a way to know, so I'm going to say I don't know.
And it may be that with our scientific tools, we may be able to probe at exactly that question, which I really look forward to.
Yeah.
That's a very interesting part of that question. And what do you think is the most beautiful thing?
Well, for kind of a hokey answer, I'm going to say my new kitten, TT, is the most beautiful thing. But to give a better answer, I don't know, just the complexity of the world. Just so many things are happening and it all ends up working. Like the sun rises, the sun sets, it just keeps going on. And I think that's kind of beautiful.
Yeah.
But also TT, my kitten.
Yeah. You are interconnected with your cat. You know that when you walk home, you know there's a deep emotional connection that happens with that cat.
Maybe so, but to the skunks and the deer I see on my drive home, I am not connected. They affect me, but I am not connected to them.
And it may be interesting to hear how your perspective may change on thoughts like that in the future.
Yes.
Maybe. So
People change, thoughts change.
yeah. It's interesting how you think that you're interconnected with your cat, but not with the deer or the skunk. That's interesting that you like pick things to be interconnected with, but not others. Like the trees that breathe out what you breathe in, you're not interconnected with them.
No, they affect me, but I'm not interconnected with them. Like,
That process isn't an interconnected process when they breathe out and you breathe in, like, and you breathe out and they breathe in. That's not a interconnected process. It seems so like semantic.
yeah, I think this is mostly a semantic disagreement, probably, in that I feel like connectivity has a lot of weight behind it. So for something, to me, to rise to the level of saying connectivity to something, that's a pretty hefty goal. And I can't say I'm not connected to the skunks I see on the drive home.
And it may be that ever since the first moment, everything is and has always been and will always be interconnected.
It could be.
And it may be that when the child is born into the world, that the child knowing that they are interconnected and having parents and community and lifestyles around feelings of interconnectedness could heal all of the problems that we have. All of the excessive self-dealing, all of the treating nature like shit, all of the mental health problems, all of the economic machinery and people feeling like they're squares trying to be pushed through circular holes in the economic machinery.
Yeah, absolutely. I think just better understanding kind of how you fit into to everything else, and being cognizant of how the decisions you make and the choices you make, how those affect other things and other people. That's important and a great way to make the world a better place.
Being aware of how you connect to everything else.
Being aware of how you affect everything else.
Luke Hawkins, thank you so much for coming on the show, brother. Thank you.
Thank you very much.
Thank you. It's been such a pleasure. Really appreciate you so much. It's so cool. 10 years later, the bros are together doing a podcast after working at the Green Bank Observatory for 3.5 years. After doing this show for 2 years, we got together to do this show. After all of our fun endeavoring in high school, I'm really happy we connected on debate. That's actually a big thing. Seriously.
Yes.
Debate was one of the most influential things that both Luke and I ever did. And
highly recommend it.
Yeah. Highly recommend. Our world cares more about debate and nuanced dialectic. So thanks everyone for tuning in. We greatly appreciate it. We'd love to hear your thoughts in the comments below on the episode. Let us know what you're thinking about probing the cosmos in general. Let us know what you're thinking about astronomy instrumentation in general. Check out the links in the bio below to greenbankobservatory.org, also their Facebook, Twitter, and LinkedIn pages. If you want to, you can email Luke as well. Also, thank you, Ori Shapiro, for co-producing. Greatly appreciate it. Thank you. And for all the great giggles in the back. And also, support the artists, the entrepreneurs, the leaders in your communities that you believe in. Support them and help them grow. You can find all of our links in the bio below on PayPal, Patreon, cryptocurrency. Help support us. Even those little donations help a lot, please. You can design cool merch and get paid. All those links are in the bio below. And go and build the future, everyone. Manifest your dreams into the world. Build that next world. Tap into those feelings that we talked about on the episode. We love you very much. Thanks for tuning in. We will see you soon, everyone. Peace.